Hi all. So let me move this thing over here. Okay. So I'm going to go through the notes, some examples from the notes that we did in class. So remember that we did this problem, what is the weight of the sign? You'll see that there's this picture with tension forces, which means likely hanging from some string. Each of the tension forces are have the same magnitude, and they're in exactly the same, but in different directions, the same angle from the x-axis. And we have to remember that weight, the weight of something is the force of gravity. So when we're solving for weight, we're solving for the force of gravity. The other thing to note here is, and it's not mentioned specifically, but because we have seen pictures hanging on walls in our lives, we understand that in this case, it'll be at a constant velocity of 0 meters per second, right? It's not going to be moving. And it's a constant velocity of that, which means its acceleration is 0. And most importantly for this problem, net force is 0 newtons. And why does that matter? It matters because this object is in a state of equilibrium. Its F net is 0, which means, as we've noted, there is going to be some sort of force of gravity. And there's these other forces that are not straight up or down and not left or right, but have some X component to them and some Y component to them. Okay. And between these X components, we know it has to balance out in the X direction. And between these Y components, as well as the force of gravity, it needs to balance out in the Y direction. Now, what's useful about this is because these two forces have the same magnitude, because they're at the same angle, we can therefore know that this X value, if we were to figure out the component vectors for these forces, these X values would be of equal magnitude. Certainly this would be in the negative X direction and therefore cancel out to be 0, right? The sum of all forces in the X direction would be X plus negative X over here. There's no other X forces. And in the Y direction, sum of all forces in the Y direction, we have Y plus Y here plus force of gravity, which we know will be a negative value. Okay. We also know that this will be 0 because F net is 0. And so by recognizing that, we can then say, oh, well, if we just find one of these Y components, we know that these two add together and then cancel out the force of gravity. So how do we do that? Well, remember that one of our equations for component vectors for the Y component is that you have the vector magnitude sine theta. So we can say, okay, 50 sine 30 happens to be 25 newtons. So it is this cord that's pulling in this direction is giving a 25 Newton value in the upwards Y direction. And we know that this will be the same. So we know that 0 will equal 25 plus 25 plus the force of gravity. We can solve for the weight to be negative 50 newtons, or force of gravity there. All right. See if I can change slides here. So we can solve a difficult problem and by simplifying it. Before, when we've looked at free body diagrams and we've calculated the normal, or the sum of all forces in the y, the sum of all forces in the x, everything's been up, down, or left and right. But here we have now a force at some angle. And we can simplify this so that we still can do sum of all forces in the x and sum of all forces in the y by, instead of doing this applied force at an angle, we separate it into its component vectors using our trig functions. Okay. And then we can figure out the sum of forces. We could say, okay, what is that? So note that the sum of all forces in the x direction is for friction. Actually, I'll do it this way. Right? Is the force of friction plus the applied force. And I'm just going to put in the x direction there. Those are the only things in the x direction. And in the y direction, we have the normal force, the gravitational force, and the applied force in the y direction. So, okay, is there net force in the x direction? Remember, friction in this case, if we think of a coordinate system, will be negative. The x direction, 69.3, they've calculated for us. All right, so that ends up being what, 29.3 newtons in that positive x direction. In the y direction, okay, so we have a normal force of 58, a gravitational force of 98 newtons, and then a positive y force from that applied of 40, which ends up being 0 newtons. So it's not, it has a net 0 newtons of force in the y direction, so it's not going to be accelerating in this y direction, but it does have a value, a positive value of a net force in the x direction. So that's an important thing there. So let's do this. Oh, one last thing. So why is the normal force not equal in magnitude to the gravitational force? In the past, we've seen, we've generally assumed that we can find gravitational force. And remember, we can find, if we know the mass, we can find gravitational force by using Newton's second, right? Force is mass times, force of gravity is the mass times acceleration due to gravity. And we've generally assumed that the normal force is going to be equal to an opposite, the force of gravity. And in this case, notice that it's not true. And yet, per my most recent calculation, it still has a net force of 0 in the y direction. And why is that? Right? This is perhaps on some sort of surface that's providing this normal force. And the reason is because this applied force has a y component, the surface that this object is on does not need to push up as hard, okay, or to push up with as much force in that y direction. And so this surface is pushing back on this object, but because the object is in part being pulled upwards by this applied force, the surface doesn't need to push as hard either. Okay, so notice that when we have situations like this, we cannot necessarily assume that the normal force is equal to an opposite, the gravitational force. It might be, but it might not be. So let's do this one. What is the net force? Okay. So I know that I'm going to want to separate this into x and y components. All right, so the x component is going to be the applied force cosine theta. So that's 150 cosine 30. And if I take out my handy dandy calculator, 150 cosine 30, I get 129.9 newtons. And the y component will be that applied force sine theta, which, okay, is 150 sine 30 in this particular case. Is 75. Okay. So now I can say, okay, what's the sum of the forces in the x direction? What's moving in the x direction? We have the force, or sorry, what's pulling in the x direction or pushing? We have the force of friction is solely in the x direction. And then we have the applied force in the x direction. Giving myself a coordinate system that makes the force of friction negative 60 newtons and an applied force in the x direction of positive 129.9 newtons, giving me a net force in the x direction of 69.9 newtons. Let's do the y direction. In the y direction, we have gravity, we have normal force, and we have the applied force in the y. Again, using my coordinate system, force of gravity is negative 196 newtons. The normal force is positive 121 newtons. And the y component of our applied force is 75 newtons. And so adding that together, negative 196 plus 121 plus 75 turns out to be 0 newtons. So our overall F net happens to be in the x direction and is 69.9 newtons. Okay, so again, like adding one of these angles certainly could look challenging, right? But all we're using is our trig functions. We're separating it into its x and y components, and then adding up all the x's, adding up all the y's to get an F net. All right. Last problem. We're adding in, bringing back and adding in some of our, fan favorites from previous units. Find all the missing values. Okay. Well, where do we start? I think we actually are only given this one force, right? We're only given this one force in terms of its magnitude. We're given this angle. I would personally start at the force of gravity, or the gravitational force. All right. So knowing that the mass is 10 kilograms, I know that I can find the force of gravity as the mass times the acceleration due to gravity. So that's 10 times negative 9.8, negative 98 newtons. Okay. Now, we're assuming something here based on the problem that in the other examples that we've had, it is on a surface. So we're going to make the assumption that the F net in the y direction is 0, that it's not being pulled upwards, but that it is perhaps being pulled to the side and moving across the floor in the x direction. So I'll go ahead and make that assumption and provide that clarity for us. Now, how does that help us here? Well, if I think about the other things in the y direction, we have force of gravity, we need normal force, and we need the y component of the applied force, which we can get using our trig functions. So to get the y component, remember it's going to be the magnitude sine theta. So in this case, 60 sine 30 is 30 newtons. And so knowing that the sum of the forces in the y direction is 0, knowing this is negative 98, and knowing this is 30, we can solve for that normal force. By pretty much pulling over the negative 98 and pulling over the 30 to the other side of the equation, which ends up getting us a normal force of 68 newtons. Okay. Let's do it for the x direction. Now, the other interesting thing that we're bringing back here is coefficient of friction. All right, so we need to remember our coefficient of friction equation, which is that the force of friction was equal to the coefficient of friction, either kinetic or static. This is going to have some sort of net force, so we'll call it kinetic, times the normal force. Okay, so we just solved for our normal force. Now we can use our coefficient of friction to solve for our friction force, 0.3 times 68. So that means our force of friction, 0.3 times 68, is 20.4 newtons. Solving again, getting net force in the x direction. Our x direction forces are friction, and the applied force in the x direction, which again, given a coordinate system, makes this negative 20.4 for friction. And we need to figure out our applied force in the x direction, which is the magnitude of the force times the cosine of theta, which in this case is 60 times the cosine of 30. And then it ends up being 51.96, we could just round that to 52. Okay, because if we take it just to 59 and round, it'll be 52. Okay, so our applied force in the x is 52. That makes this an overall sum of forces in the x direction of 31.6 newtons. And that makes our F net. So we do have a net force in the x direction of this value. Okay. Can we find acceleration? We can certainly do that, remembering Newton's second law. Where F net over m equals a. And so we have our F net We have our m. And so our acceleration is 3.16 meters per square second.